Hi guys, today I'll be sharing about duct static pressure calculation. I'll go through and explain what is static pressure, what component will lead to pressure loss, and a step-by-step guide on how to determine fan external static pressure. So when we talk about static pressure, we actually means this one. We can always see this one, static pressure. What is this means, right? This is for the fan. So basically, external static pressure is the fan strength, is the strength of the fan to push the air until the very last diffuser, or in this case, pull the air, because this is toilet exhaust fan, pull the air from the very last diffuser. If you don't have enough static pressure, you don't have enough fan strength, you won't be able to draw air or push the air from the last diffuser. The air maybe will lost somehow in the halfway. We don't have enough pressure to reach to the very end of the duct. So static pressure, not just fan, it's actually fan, but for some beginner there's a misunderstanding. It's actually everything. You see, toilet fan, we have exhaust fan, even the fan coil unit also have static pressure. Inside there's a fan. And air handling unit is very popular. We need to design the fan. We need to let the manufacturer know what is the external static pressure. Then they will select the fan based on that. And of course, the big fan, the smoke spill fan, the XL fan, right? All those will require us to determine the static pressure and let the manufacturer know so that they can select the right fan type and model to do the job. So when we talk about static pressure, the ultimate goal is to determine the external static pressure of the fan, right? So how do we calculate that? So basically, it's made up of three elements. The first thing is, inside a duct there is friction. Air passing through the duct, the surface, there's friction, right? This is very natural things. So we are talking about straight duct. You might heard of it. We call it the straight duct friction loss. But actually, duct fitting also have friction loss. They also made of metal, no? They also have surface. So when you pass through some fitting, for example, we're talking about elbow, some duct reducer, they also have friction. So when we calculate this duct friction loss, we actually need to measure the length, include also the duct fitting. We cannot just measure straight duct and exclude the elbow. No, we have to measure the whole stretch. Then we calculate from there. Then the second thing is the fitting one. No? This one is very famous. People talk about it all the time. Fitting, they call it the dynamic loss, or we can just say fitting loss lah. This is we're talking about elbow, reducer, and also the T branch. And there's a lot of different fitting, right? Fan outlet fitting, or we have canvas. We have a lot of different stuff. So that will vary very greatly lah. Depends on where are you from and what is your practice and how people do the work at your place there. Nonetheless, elbow reducer and T branch is the most basic one. All the duct work, we mostly have all these three components. Then the third one we want to include is the equipment pressure drop. Equipment, we are talking about grill, diffuser, damper, VAV box. All these things, they have resistance, or all this will cause pressure loss. So we add up all these three, then we have a total pressure loss. Then we select a fan that has more external static pressure than this pressure loss. Then we will be sure that the fan have enough strength to push the air until the very last diffuser. Okay, let's look at one example and I'll show you what I mean by friction loss and all those dynamic loss. So this is a very basic toilet fan duct layout. So let's start with the friction loss, right? The easiest to do. What we want to do is very simple. We want to split the entire stretch of duct. First, we want to know that which duct is the furthest one. See, this one, we have this path, right? We have this path, then we have this path. We also have this path until here, and also the one at the... Oh, obviously, this one is very easy. This is the longest one, right? Okay, as you can see, I already measure for you. Alright, let's just get rid of all these things first. Okay, so this is the furthest one. So we will calculate everything along this stretch, right? Because the idea, not the idea, the principle is, if your fan can in this case is exhaust the air from the longest path. That means other path got no problem. So we always aim for the longest path. Alright, so now we have 4 steps. First, we want to split all the duct by their duct size first. Then for each of the duct size, we want to measure how long is that duct section, that duct size how long, measure the duct length. Then we want to know this section, what is the airflow that this duct is carrying. Then we use the Darcy equation. Okay, the equation is more complicated. Later I will show the step by step. So here I give you a summary. This is I already measure for you. Okay, this section you see 150, 150. This is the duct size. Then I'll measure this one. Just use AutoCAD to measure. You see, measure until the center of the fitting. This is larger, right? So you have to measure the enlarger as well. You cannot just measure the straight duct and ignore this one. Okay, so measure the whole thing, and this one also include the whole stretch because they are all the same size. Then until here, after the fan also, this one also we have to measure the size, right? So everything you add up, you see, you give a summary, you organize by duct size, then the airflow is like this. This one 150, 150. So here there's one grill, so this duct will carry 100 CFM. Right, 100 CFM. After that, become this size, right? This size, this grill also carry 100 CFM. So now this one become 200 CFM already. Then this stretch, alright, before passing this branch is 200 CFM. After that is this one is 150, so become 350. You take which one that is contribute the most. Alright, so this is the whole thing is 350. Then after joining, you increase this one again, 150. You increase to 500 already. Then before the fan and after the fan will be the full CFM of the fan. This one 200 come in, then become 700 all the way out. Alright, this is how you categorize it. Okay, once you have all the data, right, then we have to apply the Darcy friction loss equation. Okay, this Darcy equation is outlined in the X-ray handbook, so it's a sound method for us to calculate. So this is the formula. It's a very complicated formula, but basically the very easy way is we calculate the DH. DH is the hydraulic diameter. So this is the formula. A is area. This one is a bit weird because we want to use millimeter. Alright, usually we convert everything to meter, right? So but for hydraulic diameter, we maintain at millimeter. So okay, let's say we calculate for the first one, the first section. So this is the area, we just multiply, then P is perimeter. Okay, just add everything together, then we get 150. This hydraulic diameter. Next is we calculate the velocity, Q over A. Q is in meter cube per second because we want meter per second. Now we have CFM, 100 CFM, so we just convert to the meter cube per second. Then this time we want to use meter, so we divide by the, see, we are focusing on this one, so everything we want to take data from the first duct section. 150 times 150, so it's 0.15 times 0.5 equals to 2.1 meter per second. So this is the velocity. Next, Reynolds number. Reynolds number is something to do with laminar and turbulence flow lah. So at this equation, they will account for that. So anyway, we'll just apply it. DH 150, V 2.1, and 1000 is just a constant, 1000. V, this is kinematic viscosity of air, is a fixed value, so you just use this one, 1516. Then you get this is the Reynolds number. Next, friction factor, this formula. If you have read the X-ray handbook, they actually suggest a core book equation. That equation is even more complicated, and that equation will need, mostly they apply in software because the equation cannot solve directly, right? Mathematics we want to solve directly, right? But the equation is both sides got F, then you have to try out, keep guessing which number until both equal, then that is your friction. You use software, you can do it, but if you want to do manual calculation, how long you want to guess until you get the number. So we have to use an alternative equation. There's a lot of alternative equation. You can Google it, the Kohlberg equation alternative, there's a lot, right? This is a very easy one, so we can just use this one. Alright, so E, this one, small e is absolute roundness factor. This is where we will account for the material of the duct. If you are using GI duct, okay, whether it is rectangular or round duct, we use 0.09 mm. If you are using flexible duct, because flexible is rougher, then you use 0.9 mm. Okay, you just substitute this one in. Then DH is a hydraulic diameter, 150 again. The 68 is constant. Then Reynolds number, power. Then we get this one is this F apostrophe is the before and after. This is the initial friction factor because we want to apply this rule. If this is more than 0.018, then this will be the friction. This will be this F to put inside the Darcy equation. Otherwise, we want to use this formula to calculate the actual F that we want to put inside the Darcy equation. So since this one is already more than 0.018, then we can go ahead and put this one inside the big equation. So everything go inside here, then we get the friction loss for this particular duct section, 0.55 Pascal per meter. So the next part, we calculate the duct fitting dynamic loss. So this will be the formula we want to use. Now mostly it's the same, but this CO is the loss coefficient. So this is the one that very difficult to get. We don't know how to get it, very hard to do. So let me show you. So here I have the layout just now, okay, our earlier layout. Now we start with the first fitting. See, we want to start from here and go all around, right? So the first fitting is this duct transition. This one, we can refer to this S-Ray 2009 Handbook of Fundamental. Under the duct design chapter, they have a few tables. So this is one of the table, and because our system is a exhaust system, so we have to refer to this ER one, exhaust rectangular duct. If it is a supply, then there is a SR one, supply rectangular duct. So to apply this table, the first thing we want to see is this AO, maybe it's original. So AO over A1 basically is this one. You have to refer to their diagram to see how to use. So you see here is HO times WO. So here will be AO, here will be A1. So basically it's before and after. Before divided by after. So you see our one, the transition is 150 to 300 times 250. So you just divide it, you get 0.3. So you see here 0.3, we don't have 0.3, so we just use 0.25, the nearest one. Alright. So the next variable is this one, theta, angle, the angle of the transition. So if you are following the SMACNA duct construction standard, right, for enlarger, small to big, right, they say cannot be more than 60 degree. If it's big to small, is 45 degree. That's the maximum lah. So you can design whatever you want. The angle is basically, it depends on how much space you have. See, in our case, I measure in the AutoCAD there. Here the angle is 14 only. The smaller the angle, the longer this length, right? And also the smaller the angle, your pressure loss will be lower. So since now we have this 14, we just find here. This one is 15, we use 15, then is this one 0.25. So our CO, loss coefficient, is 0.19 for this duct transition. Then we have to apply this formula, alright, the dynamic loss formula. We need V, velocity. So velocity, there will be different, different duct transition have different velocity. And we want to refer back this diagram again. Velocity, you want to take the velocity before going to the transition, because the Q is here. So before it is 100 CFM, okay, here 100 CFM. So we just use this 100 CFM, then this is the conversion. Again, we want to use meter cube per second. Then the area of this section, so this is our velocity. And put in, then we have our pressure drop. Okay, let's look at another example. So after the duct transition, another transition is the same way to do, and now we have a elbow. So how do we do elbow? Elbow, we refer to CR 3-1. C is common. So supply, return, exhaust, or you can use this one. So elbow, the first thing we want to know is the radius of the elbow. You can see, you measure here to here is the radius. Alright, so R over W, okay, again, also the same, I measure from AutoCAD. The radius I get is 337 mm. So I divide by the width. Width is this one, you see? This is the duct size, 250 times 200. So the width, then we get 1.3 something. Again, we don't have, and this one, I think is leaning more towards the 1.5. So we just use 1.5. H over W, simple things, 0.8. So 0.75 and 1.5, 0.19. Okay, so CP is 0.19. So CP of 0.19, the next thing we want to apply an angle factor. Okay, so we want to know the theta. Okay, so now the angle, because this one, our one is a 90-degree elbow, so it's just 90 degree. Here, the K value for 90 degree is 1.00. So there's no correction factor. Alright, so we just multiply by 0.19. If you're using 45-degree elbow, so you have to multiply 0.6, basically it's 60%. So it will be the loss coefficient will be lesser. So it's smoother. So again, we apply the same thing, everything goes the same, and we have the pressure drop, right? So let's look at another example also. So this time we have a T branch. You see here we actually have a T branch before the elbow. If you go ahead and calculate, actually, because you see T branch is like this. This is the one that we want to calculate, right? So this become the main, the main, and this become the branch. So when branch go into the main, we are calculating the main pressure loss, right? This is actually negligible. You can try and calculate later. It's negligible. So what we are calculating here is this one. You see, our duct merging into this section, and you see here, the diagram they show is this is the main, then this will branch in, right? So it's just like our fitting here. This is the one that going straight, then we branch in. So actually our one is a branch. It's not, just now you say this one is the main ma. So now we become a branch, we branch in. So we want to look at the branch one. So branch one is they put B as the branch one, S as the main one. So here I got two table. The top one is the B one and bottom one is S one. So we want to use this CB one for the branch loss coefficient. So everything we just calculate from here. So QB, QC, so it's the airflow. So we just want to measure the airflow. B and C. B is at the branch and after merging. Branch and after merging. Okay, so 350, then after merge with the 151 become 500, so divide 0.7 and our CB is 0.85. Again, apply the same thing, then we get the pressure loss. Now I want to show is the duct transition, but this time is the supply one. Just now I say we use the return and exhaust one, right? Now is we use the supply one. So this one is SR. We are calculating this one after the fan, and this one transition to the external louver. This is the last part. Alright, so the procedure is the same. Now we do all the same thing, and the angle this time is more. This time is a very high angle, so you can see the loss is very high also. But we have to refer to the supply table. We cannot use the exhaust table. It will be slightly different. So we get our pressure loss. So now that I've go through the basic, duct friction loss, how to calculate, the fitting dynamic loss, how to calculate, I will show you the summary, the result, right? So this is the earlier table. We stop halfway. Then after that, you just use the Darcy equation to calculate, the velocity, the friction factor. Then you get the final friction loss. So just now we calculate 0.55 Pascal. Then you just continue to calculate for the other duct section by the duct size, and this will be the result, 5.31 Pascal. Then because you see straight duct, after that the site might have a bit different things, so we want to apply a safety factor. So usually we just use 15%. Then we have a grand total 6.09. Not much, Alright. So the next one is fitting loss. Earlier we have calculated a few. Now I include all of them, and this two duct transition is doesn't have any pressure loss. It's normal. Then again, we also want to apply some safety factor. Then we get 28 something of Pascal. This is for fitting loss. So after that, we also want to include the equipment pressure drop. So this is the one that usually people have trouble finding what pressure drop to use for different grille and NRD, all those things. So here you can see we have one exhaust grille. This is the indoor one. Then we have this one EAG, external air grille or external louver, and complete with NRD. NRD is non-return damper, so it's to prevent the outside wind to blow air into the fan, which can damage the fan if the fan spin in a different direction. Because this is level 8, it's quite high, so we have a NRD to block the outside air from coming in. Only allow one direction airflow. And also insect screen, prevent the bugs to come in and do nest here. So if you don't know how to determine the equipment, or usually it's not don't know how to determine, it's because during design phase we maybe don't have so many time to go through one by one and find out actually how much pressure drop to use. And also during design you want to tender the project, so you don't know actually what brand or what model diffuser grille damper to use. So you can do a quick estimation using this value. Grille is 25 Pascal, external grille we give it higher, 50 Pascal, damper, all sort of different damper, motorized damper, volume control damper, we use 25. Okay, if you have diffuser, if you are designing for air conditioning diffuser, also you can use 25. Alright, so now we have 100 Pascal for equipment pressure drop. Okay, now I'll share about where do you get the equipment pressure drop. Alright, instead of estimation, let's say after that maybe the contractor or you are the contractor, you have selected the actual grille brand and model to use. Okay, so this is the one, this is the manufacturer, they give you this performance data, you already confirm to use this model. So now we see exhaust grille here is 100 CFM and the size is 200 by 150 mm. So we see here grille neck size, whether we have 200 times 150 or not. We don't have, we have this one. Also we can use this as a reference, 150 times 250. So we have see here, okay, flow rate. Okay, here I already convert for you. 100 CFM is 47 liter per second. So here you see liter per second, this minimum is 70, so we're not even 70 yet, so it's half. So you pull down this one to our grille size, you can see the total pressure loss is 17 Pascal for if your airflow is 70 liter per second. Now our is less, so maybe I would say it's about 15 Pascal. The actual one is 15 Pascal, right? So let's go for another one, is external louver. Okay, the external grille size 500 times 350. So we can use this one, 300 times 500. The airflow is 331 liter per second, so is around here. Alright, 280. This one is 560. So it's in between here. So here we have two total pressure loss. We have 1 and 2. Okay, you see this manufacturer, they say if this grille is used as intake, then you refer to 1. If it's discharge, it's 2. Ours one is discharge because toilet exhaust. So we see this one, we see the discharge number 2. Okay, maybe it's 15, 58. I would say it's 20. Go, maybe it's 20, maybe 25, 20 lah. Okay, so it's 20. So next we look at damper, NRD, non-return damper. So damper usually they give in a graph format. Maybe you have a table format also can. It depends on the brand. So here, okay, we don't have velocity. This graph needs us to use air velocity. So no choice, we have to convert to velocity. Okay, so here I convert for you is 1.89 meter per second. So you can see here, okay, 1.89, maybe it's about here. Yeah, you go up until the line here, then you go to here. Here is the pressure loss. Well, maybe you can say it's 20 Pascal. Easier, use 20 Pascal. Then you sum up all these three components. You compare with our estimation one. You see, is 55 Pascal. If we actually selected the equipment and used the equipment performance data versus our earlier estimation 100 Pascal. So it's almost double, right? So okay, let's calculate everything. So based on design, our total pressure loss, this one is a friction loss, this one is fitting loss, and this one is 100 is our estimation. Based on estimation, we get 134.73 Pascal. So this is the total pressure loss. So when we select fan, we must select more than this one. So the recommended fan external static pressure is at least 150 Pascal. You know, static pressure, they have a few standard size. You cannot just random number. So I think the next one, the previous one will be 125. Then after that 150. Maybe some manufacturer they have 200, or usually they just jump to 250, 250. So this one in other is 0.6 inch water gauge. So this will be the one that you see here, the design one, 0.6 inch water gauge EXT external. So this is the one that they design. So let's assume after we have selected the equipment, let's assume the duct and the fitting is the same. Then we use 55. Now the fan external static pressure reduce a bit. This for small fan, 1 inch water gauge of 0.1 inch water gauge of static pressure reduction doesn't cost a lot. If you are comparing like for reference lah, if we are talking about a very big smoke spill fan, those like few thousand CFM one, comparing 0.4 inch water gauge and 4 inch water gauge, I mean 10 times, the price of the system, the price of fan itself could be double. Usually double. I see it's double lah. So to give you a sense of the costing difference, the higher the static pressure, the more expensive the fan gets. So this is how you calculate duct static pressure. Not very hard if you have an Excel sheet to help you with the Darcy equation. The fitting loss is lengthy. Alright, it's lengthy, but you know, if we can calculate it instead of estimation, then we know actually how the system will perform. And usually we want to counter check after you design, you use a lot of estimation. Then let's say the contractor, they will submit the shop drawing, the actual installation drawing. Then you see from there whether or not the duct deviate or not, the duct size, the transition, whether they change from sometimes butterfly fitting to 45-degree entrance. So you know whether or not you want to recalculate the static pressure or you want to respec the fan or not. And you see whether they submit the static pressure enough for the ductwork or not, and all the equipment. After all the selection, we want to reassess the whole calculation. Okay, that is all for duct static pressure calculation. Thanks for watching. If you want to learn more about HVAC, subscribe to my channel and also check out my online course. They are quite good for beginner to learn about HVAC. Thank you.